All right, everyone. Thank you for attending today's meetup in Baltimore. My name is Joshua Ernie, and today we're going to be talking about DataWeave 2.0. We're going to be going over some more advanced concepts, namely recursion and pattern matching, and how we can use those two concepts together to do some pretty powerful things. I just wanted to do a double check real quick. Can everyone hear me okay? If I'll assume no. I mean, yes, if I don't hear anything, and I'll just keep going. But if there's a problem, just ping me in the chat, and we'll work through it. All right. So let me go back here real quick. So I blog at journey.io. Mostly I talk about DataWeave stuff and some Mulesoft stuff at large, as well as some other products that I've been working on recently. You can find me on Twitter at journey_io, and you can find me at LinkedIn at that link there at the bottom. And if you want to reach out to me for like any questions or just say hi, you can. Best way to do that is either Twitter or LinkedIn through messages. All right. So for the agenda, real quick, we'll do an introduction for myself, a quick review of the basics, really just like 2 slides. We'll talk about looping and recursion and how tail call optimization relates to those things. Then we'll go into pattern matching and talk mainly about pattern matching by predicate expressions and by data types. Then we will move into a combined example of those 2 concepts to make some higher order functions, one of them called apply to values and the other one called apply to keys. And then at the end, I'll stop for any questions that you guys may have. So who am I, and why should you listen to me? I've been programming since 2011. I know that's not a really long time in the grand scheme of things. So I'm still pretty fresh, I feel like. Most of my experience lies in Java, Python, and JavaScript, with Java heavily being the primary one there. I mostly use Python for scripting stuff, and I used to use JavaScript a lot. I don't find myself doing that kind of work too often anymore. But JavaScript was like the language that kind of got me introduced into functional programming. I've been working with Mulesoft products for about 3 years. One of the things that really caught me onto DataWeave was I didn't really see any experts in the company or the community at the time that I started learning Mulesoft. And programming languages are something that I'm very passionate about. So when I saw DataWeave, there was some apprehension about its adaptation, because I think Data Mapper had just been deprecated and DataWeave just came out. There were some people that were worried that DataWeave was kind of going to follow the same path as Data Mapper and eventually just be deprecated for something else. However, when I started working with DataWeave, a few months into it, I started to realize that this probably wasn't a tool that was going anywhere. I really think that Mulesoft nailed it with DataWeave as far as creating a programming language that makes it easy, a lot easier to do data transformations in the scope of the integrations that we do. So I started learning DataWeave about the same time that functional programming started making sense to me. Again, I said earlier I was doing some stuff with JavaScript, but DataWeave was really, there's some restriction with JavaScript. It's not 100% functional, so you can you can trick yourself into thinking you're doing some functional things and you're really not. Whereas with DataWeave, the restrictions are a lot tighter, and for good effect as well. Just a real quick disclaimer, I don't work for Mulesoft. I've never seen the source code for DataWeave. I don't have any way of knowing 100% how the language works. So DataWeave's a black box to me. So anything that you're going to hear from me today is essentially from my mental model of how the language works and not necessarily how it 100% works on the back end. Opinions are my own, and they don't necessarily reflect those of my employer. So a quick review of the basics. DataWeave is a domain-specific language created specifically to optimize data transformations regardless of source and target formats. Most of the optimization here that I talk about is in terms of readability and ease of creating these transformations. When you start looking into imperative languages versus functional languages, it becomes apparent very quickly that there are just traits of functional programming languages that make them extremely well suited for doing data transformation, whereas that's all functional programming languages do really, is data transformation. And whereas languages like Java, where they're leaning harder towards the imperative and object-oriented side of the scale, they tend to struggle with this thing. But since we got Java 8 with streams, that's kind of been alleviated a bit. The second bullet point I think is important to remember. DataWeave is a fully fledged programming language. It's easy to think of it as a tack-on to Mule that we can use optionally, but and not really treat it as seriously as, say, Java. However, I do think it's at the point now where it's more important to start looking at it as a fully fledged programming language and think about it as such, especially when you are trying to learn new things. And finally, DataWeave adheres to the core tenets of functional programming. In other words, it's a functional programming language. You don't typically hear this a lot from Mulesoft themselves. I try to say it all the time because I think if you're going to grasp anything about the language, the first thing you need to know is that it's a functional programming language. Most of the transformations that we do are done using map, filter, or reduce. I would say like 90% of them use one of these three, and if you include map object, where that's probably like the 4 functions that I use a vast majority of the time. You should already be pretty familiar with the first two, map and filter. Those are the ones that probably get the most use. You're using map to transform elements in an array, and filter to remove those particular elements. Reduce is kind of a different beast altogether because of how general it is. So you can use it as a general purpose looping tool, and with it you can do pretty much anything with an array. However, it is particularly well suited for transforming arrays into objects or scalar values like strings and numbers, if you consider strings to be scalar values. Another really important concept in understanding the basics is that data structures in DataWeave are immutable, meaning that, like within Java, where we have a class and we have getters and setters, and we can use those getters and setters to modify the state of an object. That concept just doesn't exist in DataWeave at all. So you can't change anything. So the question becomes, if you can't change anything, how do you do computation? And all of our computation is done by essentially passing data to functions and getting new data back instead of modifying what we pass to the function. If you want a deep dive into the basics, which I do highly recommend, you should check out the webinar I did with Monique Magar, and that'll be on that YouTube link. I will post these slides, so don't worry about taking notes on them if you don't really feel like it. And if you need access to the links or anything, they'll all be there when they're ready. All right, so let's get into the meat of it. Iteration and recursion. So it might seem kind of silly. I'm doing a talk on advanced DataWeave, and we're talking about looping, essentially. So what makes iteration advanced in a language like DataWeave? Conceptually, it really isn't. And that's a beautiful thing, because the reason that's the case is because we just don't have to think about iteration that much when it comes to DataWeave, because that iteration is essentially abstracted away with functions like map, filter, and reduce. They give us enough functionality to cover like 99% of use cases without actually having to worry about writing the looping yourself. However, there is still that 1% that that we're going to struggle with, because when we do need to do something that's a bit more more customized and something that like we can't do using reduce, we need to use recursion for stuff like that. And I'll demo 2 use cases at the end of this presentation of those particular of that being true, where we couldn't really do something with reduce, so we're going to opt to use recursion instead. So the problem with iteration in DataWeave is that the immutable data structures, they present a barrier to using the typical iteration techniques that we use in Java, like for loops, for example. And let's look at those real quick. So this is how we do iteration in Java. This is their typical for loop, not the enhanced version. So basically you're setting, I think I have a typo here. This should be int I equals 0. Obviously I haven't been writing as much Java recently. So yeah, it should be int I equals 0. I is less than 100, and then you increment I every time we go through the iteration. And when I, as long as I is less than 100, we'll keep going. And once it's not, this loop breaks out. So there's a couple issues here that make this style of looping completely incompatible with DataWeave as we know it. First, the main offender here is the I++. The problem with the I++ is it changes the variable I in place, meaning that I is not an immutable variable. We just can't do this in DataWeave. There's no conceivable way to do it. The second one is system.out.println. Printline, sorry. The problem is not with the print statement itself. It's that within those 2 brackets that surround the print statement, you can have any number of statements that you want. And that might not seem like an issue, but one of the first things I ran into when I was working with DataWeave was that for example, when I was doing map, I'm cognizant of the fact that I'm doing some iteration, and I'm thinking to myself like, okay, well, I'd really like to print out some values to the console while I'm doing this iteration. The problem is you can't really do that because just because of the way that the language works, it won't let you do it. There are ways to get around that, mainly through the log function. But what I'm trying to get at here is that if you have to use more than one statement within one of these loops, then you're probably doing something that's just not functional, and shouldn't be used within DataWeave. And other looping constructs like while have this same property. While they don't necessarily modify values in place, they do have this issue where we can put any number of statements with side effects in the body of the loop. And if you're not clear on what a side effect is, it's basically any kind of computation that's happening that's not for the purpose of returning a value. So if we're printing out to the console, that's a side effect. If we are going out to the network, those are side effects as well. So iteration in DataWeave, which is completely functional. We can iterate using one of 2 strategies. I put reduce on here just because it's such a general purpose tool for looping through arrays and doing something with them that I do think it fits the bill for an iteration tool in DataWeave. I don't have map and filter in there because I do feel like those 2 particular functions, while they do iteration, they are specific enough that you would never really use them in place of like a general purpose looping construct. And finally, we have the most general purpose looping construct that we can have in DataWeave, and that's recursion. So what is recursion? According to Wikipedia, and this is like, honestly, I think this is a horrible definition, but I included it just because it does get at an interesting point. Recursion in computer science is a method of solving a problem where the solution depends on solutions to smaller instances of the same problem. And that part at the end is really the interesting part there. Depends on solutions to smaller instances of the same problem. It's kind of hard to conceptualize just by reading it, so I'll try to circle back on that and bring that full circle. But according to me for this talk, in DataWeave, recursion is when a function calls itself for the purpose of looping or iteration. So real quickly, let's look at a recursion example. All the examples are going to be DataWeave 2.0. However, I should point out that these are easy enough to do in 1.0 as well, but there are some slight differences, and I'll talk about those when we get to the tail call optimization section. So var range 1 to 10, this is basically just going to give us an array of values from 1 all the way up to 10, incremented by 1. And we have a function here called recursum. And basically what this is going to do is take in an array of values, and it is going to add them all up. Array of numbers, rather. So you'll notice here, first thing we do is check if the array is not empty, because if it's empty, we just want to return the total, which we set to 0 up here. This becomes, the fact that I'm setting essentially the return value here and passing it in as I go is going to become really important later. And finally, what you'll want to look at here is we're actually calling the function that we're defining within the definition of the function itself. So let's dissect this function a little bit, just in case if we need a recursion refresher or we're just not that familiar with it in the first place. It's like a deceptively simple concept, but I remember the first time I ran into it, I was it took quite a bit to really grasp it. So again, we're passing in an array, and we are setting this optional parameter. We're just setting it to the total is equal to 0. I call these in the recursum. You'll notice that I'm passing essentially the rest of the array. I'm popping. I'm no longer interested in the first value. I just want everything between the second value all the way to the end of the array. And I want to pass that to recursum. And then finally, I want to take whatever I have for total. I want to add the first value of the array and send that into recursum again. This if statement is incredibly important because this is what keeps us from going into what's called infinite recursion. If you don't have these kind of if statements that let the recursive function know when to stop, it'll just keep going. You'll get a Stack Overflow and the program will crash, or where sometimes it just hangs there for a while before it crashes, and you're not really, it's just completely silent, and you're not really sure what's going on. If that happens, for example, you're running your code, you have some kind of recursion in there, and it just stops, and nothing seems to be happening, there's probably something wrong with the recursive statement that you're writing. In this base case here at the bottom, this is essentially whatever we're going to be returning when we're done with going through the loop. In this case, it's the total. So you'll notice that I'm essentially accumulating the total by just passing it through to the function every time. So just a brief aside, looping with reduce, it's really important to point this out here because most of the times when you are looping with recursion, you can probably get it done with reduce, and it's probably better to do so as well, because with reduce, you don't have the potential to shoot yourself in the foot with what I was talking about earlier. You're not going to run into the problem of infinite recursion because of the way that reduce is set up and written as a function, it just goes through the array. It's not doing any kind of like callback and so on and so forth. Not callback, but call to itself. And again, I just want to reiterate, I don't know what the core is doing. I don't know what I don't know about the DataWeave source code, but I'm fairly certain they're not implementing reduce with recursion, but they could be. I don't know. Point is, it really doesn't matter. So if we want to do it with reduce, you'll notice kind of the same thing we have here. We instead, the array gets passed in here, but we do have this total that we're using to accumulate as well. So I think that's interesting to point out, and we'll kind of look at that a little bit more when we talk about tail recursion. Last point of this is, if you can use reduce instead of recursion, you really should do so. Just one, because it's safer, and two, because it's probably going to be easier to understand. Recursive functions tend to be one of those things where, like, once you get it, you have an aha moment, and you have that understanding, but they tend to take longer to understand unless you deal with recursion on a daily basis, because we're just so used to iterating and thinking about things from an imperative perspective, like with the for each loop, or the for each scope rather, in Mule, that we don't get as much experience using recursion, and other programmers don't either. So I do have a tendency to avoid recursion if I can, and I do recommend that other people do as well. So problems with recursion. If you're not careful and your language doesn't support tail call optimization, you can run out of memory. This is what a Stack Overflow is, essentially. So what is tail call optimization? It's an optimization that the language implementation makes. So it's not something that you can, like, if your language doesn't support tail call optimization, there's nothing that you can do about it, unless it's a language like a Lisp and you can write that stuff yourself. But in language like DataWeave, we don't have that level of flexibility. So if your language doesn't support tail call optimization, just be aware that you could essentially blow the stack doing a perfectly normal recursion. Tail call optimization is supported in DataWeave since 2.0. So that's really important to know. If you're working with really big objects and trying to iterate through them using recursion in 1.0, there is a chance that you could blow the stack. So in that particular case, Java might be a better tool to reach for and just do standard iteration. So just kind of keep that in mind. If you're going to be doing if you're going to be going over a really big piece of data using recursion with DataWeave 1.0, it might be safer to use Java instead. But I've done recursive stuff in 1.0 and I haven't had any problems. So just kind of, use it judiciously. So we talked about tail call optimization. We know what the optimization, we don't really know what it is. So let's talk about that real briefly. It's basically so when you're doing recursion, you just start putting more and more and more and more on the stack. And what tail call optimization does is it basically is an optimization that happens, and it takes the recursion and turns it into iteration instead, much like a for loop, so that we don't have to keep this state track of the iteration tracked in the stack. So a tail call is a call to a function that is performed as the final action needed in the function body. This is a lot easier to see than it is to talk about. So let's check out some examples real quick. So on the left here, we have an example of a recursion where the recursion is happening in tail position. And on the right, we have an example of essentially the same. Functionally, they're the same, but on the right-hand side, we don't have that recursive call in tail position. And so let's dig into those real quick and talk about why the one on the left is in tail position and why the one on the right is not. So if we look at the one on the left, which is the same code that we were looking at before, you'll notice that after recurSum is called, there's nothing else that this function needs to do. It's it. It's the very last, like I was saying earlier, it is the final action needed in the function body once we get to here. And if for some reason we get to the end of this array and this returns false and we go to the else, all we do is return the total, and that's it. So DataWeave can optimize this one on the left for tail call recursion, but it can't do it on the right. And let's look at it for a second. So again, we see in this case, I'm not passing in, I don't have that that optional parameter total. I'm just asking whatever client of this function to pass in the array. We have the same kind of if-else statement. However, if you look at the line where we're actually doing recursion, you'll see that after we call recurSum, we have to add a value to whatever it returns. So this means that we can't do this tail call optimization. Like if there was a compiler, the compiler wouldn't be able to do it, because after this guy gets called, we still have to do something with that information. So once we get to the end of the array, we have to go back and unwind the stack, add all of these back together, and return them. So that's about it for recursion. We're going to come back to this later when we and look at like a practical example of how we can use that. So for now, let's talk about pattern matching. So what is pattern matching? Most people think of pattern matching as like a more robust switch statement, which is fine. I think that's a good way to look at it. But it is important to point out that it's not a statement. It is an expression. And that's important because expressions return values and statements don't. And everything in DataWeave is an expression. So I could essentially, if we look at this code here at the bottom, starting with hello and ending with that closing brace, I could put a var x equals in front of that, and it'll assign x to world with an exclamation point at the end. So in DataWeave, we use match case in the else keywords to perform pattern matching. And again, it can return much like a switch statement, or perform much like a switch statement. So if we look here, we pass the match statement the string hello. It goes down through these cases and sees which one of them matches. Obviously, the first one does. So this just returns the string hello. If this was goodbye instead, it would return space. And if it was any other string, or if it wasn't a string at all, if it was an array or null, it would just return where am I? And that's what we get back. So there are other things that we can match on besides just strings and literal values. So we can obviously match on booleans, numbers, anything else. We can also match on predicate expressions as well. And I'll talk about that in the next slide. One of the cooler things that we can match on is data type. And in the demo, we'll be leaning very heavily on matching by data type in order to get some work done. And finally, you can match by regex too. But I'm not going to go over that in this talk. I find that it's pretty intuitive to match by regex after you already understand how the other ones work. But I do have a link to the Mulesoft documentation on regex pattern matching at the end of the slides, if you're interested in checking those out. So matching on predicate expressions. So first thing you might ask yourself is, what is a predicate expression? So it's just an expression that evaluates you true or false. It could be like an anonymous function. That's fine. It could just be the literal true or false. But the important thing to note is that it needs to evaluate to some Boolean. And with match, this predicate expression takes the form of if and then a Boolean test. There's no else, because the else is kind of implied within the match. So just keep that in mind. When using predicate expressions with match, match is going to match with the first predicate expression that evaluates to true, and it's going to ignore the rest. So that's really important to keep in mind. You can really shoot yourself in the foot with some subtle bugs, not realizing that when it evaluates to true, it's not gonna do anything else. It'll just evaluate that single branch, and then it's gonna return. It's not gonna do both, and it won't keep going. So you could imagine that each expression has a break statement at the end of it. That's one way that you could think of it. So with predicate expressions, you need to specify the name that the value to match will be referred to in the predicate expression. This is a really confusing sentence, and it's going to be much easier to show rather than to talk about. And just as a note, it's always an option, even though it wasn't shown in the previous example. So let's look at what that looks like real quick. So if we're matching on a literal here, again, we're doing a number, but we are matching with predicate expressions down here. You'll notice case n if n is less than 20. So if you decide to put essentially like an unassigned variable name after case, DataWeave is going to use that to hold the value of whatever you're matching on. In this case, n is equal to 49 in all of these cases. And if this was an array or an object, it would be equal to that array or object as well. It's just setting it there. It goes ahead and runs this predicate expression right here. If n is less than 20, here n is going to evaluate to 49 every time. Obviously, 49 is not less than 20, so we're not going to evaluate this. 49 is also not less than 40. We're going to skip that. And on the third line, we're going to hit a match. So this will return numbers less than 60, and we can use n here on the right-hand side as 49. So keep that in mind, that if you ever need to use this value, if it's a literal, for example, you can always specify a variable here that it will get assigned to, and then you can use it on the right-hand side of the match expression. This turns out to be more important if you're using literal values here on the left-hand side, because if you're using a variable here, you also have access to the variable on the right-hand side as well. So just keep that in mind, and I'll show you an example in the demo of where I'm just directly referencing whatever we're matching on in the match result. So again, we can also match on type. So we have an array of 1, 2, 3 here. We call match. Case, if it is an array, we have an array. If it's an object, obviously this one resolves to an array. I know this doesn't really seem like a huge deal that we can do this, but I think once you see the demo and some like the more powerful things that we can do when we match on type, hopefully it'll be more exciting. All right, so now we're going to get into some practical examples, combining pattern matching and recursion to navigate nested data structures. So, and by nested data structures, what I mean is just like let's say we have an array, and it's an array of objects, and some of those objects have arrays, and in some of those arrays there's objects, so on and so forth. This can happen who knows how many times. Let's say that we don't know. I would refer to that as an ambiguously nested element. So use case number 1, we need to build a utility function that will modify all the values in an element, regardless of how deeply they're nested. In this case, an element is going to either be an object, an array, or any combination of the two. We're not expecting to get any kind of scalar values like strings or numbers as input into the function. So how do we approach something like this? So we want to write a function that can be reused among any use case that needs the same behavior. And I know that seems obvious, but the reason I point it out is because we need to be able to work over objects and arrays. This particular function will not be sufficient if it only works on objects or if it only works on arrays. The use case doesn't specify what modification should take place. So we're talking about modifying values. We know that we want to modify values, but we don't know how we want to modify them. Do we want to make all the strings uppercase? Do we want to add one to all the numbers? We don't, in this function, we don't want to make that decision for the client. We want the client to be able to pass in that functionality. So we should probably take another function as a parameter, and that particular function will describe how the values are going to be transformed instead of hard coding it in. And finally, we need to determine a way to navigate through a series of ambiguously nested elements or potentially no nesting at all. So we might have a one-dimensional array. We might have an object, just like a flat object of key value pairs, where all the values are just strings. We need to be able to deal with those simple cases as well as those much more like ambiguously complex cases as well. So let's take a look at the function signature that we're going to use to do this. I'm not sure if this is like official notation or not, but it looks pretty similar to what I've seen in the past. So but I will walk you through it. So we're going to call the function apply to values. We have a parameter called e, which on the right-hand side of these colons are just the type of that particular input. So this one needs to be an object or an array. Again, like I was saying earlier, we're not going to accept any strings. We're not going to accept any numbers. But we're just going to expect them to pass objects and arrays. What I'm saying is, like, for the code that I'm going to show you later, we're not doing any kind of like error checking to make sure that the user is passing in the correct input. Fn is a parameter. It's a function. It's going to take in a scalar and pass back a scalar. Just this note real quick, a scalar is not a DataWeave type. I'm just using it to represent essentially a single value, not a collection of values. And this whole function, apply to values, should return an object or an array. And just remember that this is a brand new object or a brand new array. It's only related to the input object and array through this function. Other than that, they really have no relation. So this is how we would implement this particular problem. So we have e and fn up here, fn being the function that describes what kind of modifications we'd like to make, and e being standing for element. I typically use that to mean it can either be an object or an array. So we go ahead and we match on that e, and we want to check to see if it's an array or if it's an object, and if it's just something else completely. If it's an array, we're going to take in e, and we're going to map it. And for every one of those values, we're just going to call apply to values on it. The reason we do that is because keep in mind that at this stage in the transformation, we don't know what the array contains. All we know is that it's an array. So what we kind of want to do is like kick the can down the road and let somebody else deal with it. And that's why we do this map apply to values for every single value that's in the array. And then we just go ahead and pass the function through as well. If the case is an object, we're going to call map object, and we'll take the key and just leave it as is. That's what this is doing right here. And we'll, again, we know it's an object, but we don't know what the values are. We know we don't want to touch the keys, which is why we just leave them as is. But we don't know if these values are strings. We don't know if it's another nested object. We don't know if it's an array. So again, we're going to kick this can down the road and just call apply to values again for every one of the values on here. Eventually, depending on your data structure, we will get to the point where we actually do some work, and that's all done in the else statement. So this basically matches on essentially scalar values instead of arrays and objects, and we just call the function on e, which will transform the value of e. So what's really interesting about this is that these lines here, cases array and cases object, are really just handling the cases where we don't know what to do yet. So when it's an array, like I was saying, we know it's an array. We don't know if every value in it is something that we can do the transformation on. Same thing with object. We know it's an object, but we don't know if all the values are values that we can do the transformation on. However, when we get to this last case, we do. So some notes real quick. While the array branch of match has the recursive call until position, the object branch of match does not. So if you're going to use this code in your own code base, just be aware of that when you're using it on very large elements. So make sure that and I guess what I mean by that is make sure you're testing with some data that represents what you might be using in production. So if you're dealing with these, if you're in your dev environment, you're dealing with objects that are like 5 kilobytes in size, but they're abbreviated from an object that's typically 50 megabytes. Make sure you test it with the 50 megabytes before pushing that off into production. I'm going to break out of this real quick. Before we go over use case 2, I'm going to show you a demo of this one real quick, just so we can get a conceptual understanding of how it's supposed to be working. Okay, so I just have a listener here, and it's it'll be triggered when I call applied to values. And here I'm setting the payload, and this is just kind of like the ambiguously nested object that I'm talking about. We have an object, a simple key value pair here, but this key has an array as a value. That array contains a bunch of objects. It also contains another array that doesn't contain any objects. It's just these scalar values. So that's what we're going to be passing into apply to values. And sorry, I can't blow this up a bit more, unfortunately. But here's the apply to values function that we were talking about earlier. This is the function where I'm actually defining what I want to do with each one of those values. Don't worry about this this error here. This does compile, and it does run successfully. I think this might just be maybe I'm not giving them enough information about my types, but it runs fine. So this function upper if string, basically if the element is a string, we want to set it to uppercase, and if it's not a string, we just want to leave it. So I'm going to go, I think this is already running. So let me go ahead and I'll pull up Postman, and I'll give this flow a call real quick. Okay. All right. So let's check out what this did in contrast to the input. So we look at the input here. You'll see that the overall structure of this data has not changed at all. We haven't modified the arrangement of anything. The keys have all stayed the same as well. They're all just lowercase. We also haven't modified anything that's not a string in any way, which is exactly what we wanted. And you'll see that this will basically go through. When it first starts, we match on, let me blow this up a little bit. When it first starts, we match on object. So we're calling this particular branch, and again, it's just kind of kicking that can down the road. It calls apply to values for each one. If we look at, so it's going to call apply to values for the value world. When we get to the match on world, it's not going to match an array. It's not going to match an object. So that's when we actually do the transformation, which is the capitalization of the actual string. And when we get down here into this array, the array gets passed in. Again, we just map the function apply to values to all the values in the array. These will both hit this particular else branch because it's not an array and it's not an object. We do have a string, so we'll go ahead and do the transformation. In the case of the number, however, we hit this else branch, so we don't do anything with it. We just pass back what it already was. All right, so I got a question. Let me read this one real quick. Does match perform with large arrays or objects? Yeah, I haven't had any problems with it. Okay, back to the presentation. We'll do the, where did it go? Okay. So use case number 2. This one, we'll go through this one a little bit quicker because really the point of use case 2 is just to show you how similar it is to use case 1. So we need a utility function that will modify all of the keys in an element, regardless of how deeply they're nested. Again, an element is an object and array, combination of the two. How do we approach it? The approach is going to be the exact same. We want to write a function that can be reused across any use case. We don't really want to specify what the modification is. We want the client to pass in a function that tells our function what it should be doing. And finally, we need to determine a way to navigate through these series of ambiguously nested elements. Same as our previous function, but we'll call it apply to keys. So same exact signature. Now let's look at the implementation real quick. The big difference between these two, one of the striking similarities is that when we see an array, we do the exact same thing. We just call map and send it apply to keys for every value in the map. We don't know what to do, so we're just passing the, we're just kicking the can down the road. If it's an object, this is where things get a little more, this is where we're actually doing our work because objects are the only things that can have keys. So you'll see here that we use the function and use it to modify the key here. And then we just apply keys to everything else in the object because remember that an object can, the value can be another object. The value can be an array. We don't know. So we kick that can down the road. And if it's none of those things, it has to be a value. It's not a key. And we don't want to mess with values in this particular function because we're just applying the function to keys. So we just pass back the value as itself. One thing that I didn't mention in the notes is that I believe in DataWeave, you have to have the else statement. There are some other languages like Swift where you can like match on an enumeration, and the only requirement is that you handle all of the I guess what am I trying to say here? All of the types that the enumeration can be. So if you've exhausted all of those possibilities, you don't need else. I think in DataWeave you do need it in every case. There's a follow-up question. Can we use pattern matching for masking social security number patterns or regex? Yeah, definitely. And I don't have that example in this particular presentation because I didn't think it doesn't look like I'm going to have time to do it. But whoever asked that question, if you want to follow up with me on LinkedIn or Twitter, I'm more than happy to send you the code for masking security numbers or passwords or something like that. So after we look at use case 2 and use case 1, a pretty obvious pattern starts to emerge. I mean, the shape of these things is almost identical, but the real gold here is to notice that when we're going through ambiguously nested elements, we don't know how complex they're going to be, but we know that we need to get through all of them. This is the pattern that you use. So with the question, can we use this for masking security number patterns? We're going to use the same thing. If we're going to modify all the keys, we're going to do the same thing. If we're going to modify all the values, we're going to do the same thing. It's always checking if it's an array, using map, and kicking the can down the road. If we're messing with keys, we're still going to be using map object for object regardless. If we're messing with keys, we'll execute some functionality on the key itself. If it's a value, we'll execute some functionality on the value. And with values, you'll call it in the else branch as well. But the point is, like, the big difference between these two is this one is just modifying the keys here and leaving the values alone. This one's touching the values and leaving the keys alone. Other than that, they're remarkably similar. So the conclusion, map and map object combined with recursion and pattern matching on types allows us to modify ambiguously nested elements and values in that element as well. So as a kind of, let me demo this real quick. I almost forgot. So apply to keys, same code, and we're going to use the same object, so we don't need to talk about that. But just note that we're just going to uppercase the keys instead of doing anything with the values. I mark this as really important because keys have their own type in DataWeave. They're not strings. They're a type of key, and you can't do string things on keys. So when you are dealing with modifying keys or anything like that, in any part of your DataWeave code, regardless of if you're using recursion or pattern matching, it doesn't matter. Just make sure you're casting that key to a string first. And I believe this is already running. We'll call apply to keys, and we should see that all the keys, hello, data, name, and name should be uppercase, whereas all the values here are untouched. Okay. And trying to, here we go. To do, can apply to values and apply to keys be modified so that the recursive call in the object branch of the match expression is in tail position? This is something I haven't tried yet. I'd be interested to know if anybody else has, but it's something that I've been thinking about recently. I just haven't dug too deeply into it. And number two, can we write a utility function that applies a function to values only when the key matches a certain constraint? And this is essentially, if the question on masking social security numbers is what I think it is, this is what we'd use to do it, number two. And actually, if I can, it would actually look something like this.